Great. So today we are going to talk about multivariate data analysis for NIR data. So why do we do multivariate analysis on NIR? So spectroscopic methods, they provide us very valuable insights into both the chemical nature of different samples as well as physical characteristics of those samples. By nature, spectroscopy methods are highly multivariate just by the fact that you have so many wavelengths of data that you're looking at. Now, we most commonly use multivariate data analysis on NIR data because that's due to all the overtones and combination bands. You wind up, instead of having very sharp peaks, you have these broad general peaks. And to pull out the information that you really are interested in, you need to kind of massage the data and filter out all the noise for the stuff that you don't really care about. So some typical applications for spectroscopy, it runs the whole gamut from process monitoring and pharmaceutical blending. You can identify raw materials, identify failure rates, look at oil density. You can also do types of quality assurance, so you can predict various concentrations of things in your product. You can monitor polymer composition. Sometimes you can see polymorphs in IR. Classify fragrances. So there's a lot of applications, and one of the benefits for NIR data is there's often no sample preparation. You can just shine your infrared light directly on your sample and get some feedback directly. In some of your other methods, you do tend to need to do a lot of sample preparation before you can do anything with it. So if we take a look at our electromagnetic spectrum, if my computer will work, there we go. So what we're looking at when we're in the near infrared, our visible range is from 400 to 720, and then from 720 to about 2500 nanometers is where your near infrared is. Again, down in your mid infrared is where you're going to get your fundamental vibrations, and near infrared is where you have your overtones and combination bands, which makes you have these nice broad peaks, and it makes it a little bit more difficult to pull out the information than in some of the other schemas that we're looking at. So benefits of NIR is that it is non-destructive, so you can run spectra on your sample, and go ahead and take that into your lab and do a one-to-one sample correlation to do that. There's minimal sample preparation, and it's very easy to integrate into your process. Typically, you just need a little sapphire window, and you can put your instrument right up into your process and get some feedback right away. It also tells us both chemical and physical information. Because of the wavelength range, we can often tell some things about particle size due to baseline shifts. Now, as I've mentioned before, some of the challenges is that there are these wide spectral features that can be undefined. We do suffer from scatter effects, so it does need a little bit of pre-processing. If you're not looking at particle size, for example, we need to get rid of those kind of scattering effects. And therefore, it requires this multivariate data analysis to really understand what you're looking at. We can apply various types of multivariate data analysis to spectroscopic data. We can do exploratory data analysis and classification methods. We can do qualitative methods as well as quantitative methods. And by doing this, you can actually replace some very expensive or destructive testing, and you're able to get analysis in seconds. You can get real-time analysis, or even if you're doing it offline, you can get your results back in an hour or two, including taking the data and bringing it back to the lab to analyze, rather than waiting days or weeks for, say, HPLC testing. And it allows you to see the true structure of the data during the process. Now, one of the things that we tell you often is that you should plot your data before you do anything else. I plot my data every time I perform any sort of pre-processing on it, just to do a gut check to make sure that what I think I'm looking at is what I'm actually seeing. We often use spreadsheets to plot this data, but again, this can be very tedious and time-consuming because you have to make plots individually, and they tend to not handle plotting large spectroscopic data sets very well. In the unscrambler, we have lots of nice plotting routines that can do in a simple click what can take a lot of time in spreadsheets. We also have the ability to do some sample grouping, so we can look at patterns in our data based on different values for different wavelength regions, for example. So often what we do when we look at spectroscopic data is we do line plots. This is a good example of why we might do a line plot very initially, is to take a look at the amount of noise that's in your spectrum. We can see here that we have a scan that's kind of out of whack. So maybe someone was measuring tablets in this case, and a particular tablet was not seated in the holder correctly, and so you've got stray light coming in. If we plot it like this, we can instantaneously recognize that, mark that sample, remove it from your analysis so that it doesn't get conflated, that error, into your analysis. And you can also see, if you look a little closely, this is pretty noisy data, especially for NIR. You don't see that very often, which gives me some indications of what types of pre-processing I might want to do. In this case, I definitely want to do some sort of smoothing to kind of get rid of those little bumpy noises, because that's just noise and it's going to detract from the information that we really care about. Another way to look at your SPECTRA data is we do what's called descriptive statistics. This is under the tasks folder, and we can take a look at the quantiles. So this gives us box plots, so you can see which areas have a lot of variation and which are showing minimal variation. And you can make some decisions about whether this is related to the sampling technique or the chemistry. And I'll go into a little bit more detail later about the scatter effects. Doing this plot is really nice to help you justify doing certain types of pre-processing methods. We can also do matrix plots. If you're doing something that's like a chemical reaction, sometimes these show some very nice things. And it is a 3D plot. In this graph, I obviously can't do it in PowerPoint, but in the unscrambler, this is a freely moving, so you can go around and look at it from all angles to find what you like the best. If we're looking at a chemical reaction, as I said, you can actually watch how peaks grow or disappear over time throughout the reaction, which is kind of nice. And let me go ahead and show an example of that. Let me get the right training folder open. My apologies. Yes. So we are going to open up the unscrambler and close this. It's not showing my screen. Here we go. I'm going to import data, variant data. Here. All right, if I plot this one in the matrix format, we can see that there's a chemical reaction going on. So over time, this peak is losing intensity absorbance, and some of these are gaining absorbance. If we had plotted this in our traditional line mode. That's also very useful, but it's kind of hard to see what's happening, which one's growing over time, which one's decreasing over time. So sometimes that 3D matrix plot is really quite handy. Another thing we can do, we can look at this if I can insert a category variable here. And I'm just going to open up this. So this is just going to put some labels in here so we can see what timing that these happened. And change data type to category. All right. Now if I go in my line plot, I can sample group based on that category variable, create row sets, and that gives us a similar view to what we got with the matrix plot. So we can see that time 1 is the blue, so you can see that these are decreasing through the time and these are increasing over time. So it's just a different view of the same information, whatever makes the most sense to you. Okay. So if we're doing some principal components analysis of spectroscopic data, we start with our original data, we mean center. So we find the average spectrum and subtract that from the entire data set. And then we calculate your principal components, and principal component 1 will be the highest contributor, principal component 2 will be the next highest contributor, etc. When these loadings should be interpreted just like spectra normally would. So if you have peaks in an area that you know are due to, say, carbon-carbon stretches or carbon-hydrogen stretches or carbon-oxygen double bonds, you can interpret that directly from the loadings. Once the loadings start to look like noise, it probably is, and don't use any more components at that point. Again, so the loadings contain spectral features of your constituents, and the peaks indicate the important spectral regions for that particular component. So we can identify what's causing the changes, and so you can go through and figure out what's going on with your data by analyzing the loadings themselves. And you can see when the noise comes in very quickly. So let me go ahead and give an example using the unscrambler. We're going to close this and open the wheat data here. So this is data that was collected for different wheat, and they want to predict protein. So first thing we're going to do is I'm actually just going to do a principal components analysis. I always start with a principal components analysis just to kind of get an idea of my spectra, get an idea of my data, see if there's any groups, any gross outliers in that data. Even if I'm going to do a regression later, it's a good idea to look at the principal component set first. Okay, so this is pretty nice. We've got a 1 PC problem here. So this is my general loadings that we are seeing in our data set. Now, I was bad here and I did not plot my spectra initially. So let me go ahead and do that now. And this is what our spectra looked like. Okay, when we did our PC on this, PCA analysis on this, this makes sense, right? Because the maximum variation that's happening is just happening basically by an offset. So we definitely need to do some sort of pre-processing on this data before we do anything else. If we go in here, we can sample group based on our protein levels. And we can see that they kind of all overlap here. So we need to do something. Now, my first step when I look at this kind of data is I do Analyze Descriptive Statistics on my spectra. And we can see there's a lot of variation here. What I'm going to do now is I'm going to right-click and look at the scatter effects. Now what this does is it calculates the mean spectrum, and for each wavelength value and each sample, it's going to plot that sample's value versus the mean. Now what we see here is a lot of offsets, okay? Everything seems to have a very similar slope. So this is telling me that there are additive scattering effects. So the scattering is the same or similar across the entire wavelength range. So we need to do something that gets rid of additive baseline effects. So what I would probably do here is a second derivative. So we can do task, transform, and a Spitsky-Golay derivative just on the spectra. And this is really nice. What we can do is do a preview result. This allows you to see what you're doing while you're doing it. So if we only do 3 smoothing points, this is still very noisy data. But if we crank this up a little bit, we can find the place where we've reduced the maximum amount of noise, but we keep our signal. I think that should be good. About 15 smoothing points total. If we say OK, now we can plot this again. And then I'll take a look at my sample grouping for my protein because that's what I really care about. And we can see there's still a little bit of overlap, but it's starting to separate out a little bit more. When I get to this point, I might do another PCA, so we can take a look at that. Principal component analysis. This is a warning that comes up when you've done a derivative because the ends, you lose the data on the ends due to the smoothing points. So don't stress out if you see this and you've done a derivative. Just say yes and it'll go ahead and calculate everything. We're still going through, a 1 PC model. We can also do our sample grouping in here to see if we see any patterns with our protein structure. And there's a little bit, but it's still kind of messy at this point. So that tells me that I'm probably going to need to do some more pre-processing before I'm able to come up with a regression model for this. I did have someone ask me about this influence plot. The influence plot tells you something about your data to say how similar the data is to each other. So the hoteling t-squared, we can put that on our scores plot. That has to do with how far from the center of the model your data points are lying. Okay, so they're in the model space, but they can be very far away if they have crossed this line. So they're kind of extreme samples. Okay, when they're going along the y-axis up here, that is describing the residuals. That's how much that these principal components don't explain about your samples. So whatever's left over, there could be other noise, there could be something that's not being modeled for those particular samples. If things fall in this area or in the lower right-hand area, it's kind of like a yellow light that you might want to check your data. But if it's in the upper right-hand corner, that's a good indication that you have some outliers because basically your sample is not being described well by the model and it's very extreme, very far away from the center of the data. So there could be something you might want to remove that from your sample. I did have someone ask me a question that says, I thought you generally do a first derivative initially and then do a second derivative. The reason why I didn't do a first derivative in this is they're a little bit trickier to interpret. First derivatives get rid of a flat baseline, and second derivatives also get rid of a curvature in the baseline. So it's just, for me, I tend to work with second derivatives rather than first derivatives unless I really need to. First derivatives get a little tricky because in a second derivative like this, the peak is in the same position, right? So this peak and this peak were actual peaks in the original data. When you're looking at a first derivative, the peaks are actually at where the lines cross zero. So it makes it a little bit trickier to interpret. And so I tend to not use them that much for that reason, unless there's a really known justification for doing a first derivative. So again, I can see that there's still some sort of, there's still noise in there that I need to get rid of. I can tell from this PCA model, and we can't really predict very well yet. So what I might do again is take a look at that descriptive statistics again. NIR data. And I'm going to look at my scattering effects. Now what we see is this fanning situation, right? So this tells me that there is some scattering that's happening, but it's different over the wavelength ranges. So there's more scattering at the higher or lower wavelength ranges than they are at the center. So now I want to get rid of something that has multiplicative scattering effects. So I go ahead and in this case, I'm going to apply an SNV to my calibration data. I'll just take a look at it. So it tightens things up quite a bit, actually. We'll go ahead and plot those and do some sample grouping based on the protein. And now we're starting to see that they're kind of pulling out. They're getting a little bit tighter. Even though there is some overlap, we don't have as much noise in our spectrum. And we can notice is that over here, if I zoom in, we're really starting to see things pull out according to the range. So I'm going to go ahead and do a partial least square on this now using my calibration data. I'm going to predict my protein. And I got a pretty good model here. It's a 3-factor model. This recommends 4. That's just based on some of the numbers. It's a slightly better RMSEE for 4. But if we look at our explained variance, which is the first thing you want to look at one of these, we can see that going from 3 factors to 4 factors really doesn't gain us enough information to really justify using that extra factor. You always want to use as few factors as possible to keep the robustness of your model. And we can see we're predicting, we've got about roughly a 5% error. The way I calculate this, the RMSEEs are in the same units as the original data. Okay, so these are protein units. So the way you see this is that if I have a prediction of 10, I've got 10 plus or minus 0.5 protein units. So I just took 0.5 divided by 10, and that's roughly a 5% error is where I get that from. And that's pretty nice. And we can compare that to if we did our analysis on the raw data. And we'll see we get a very different look. All right, it's taking more than 7 factors, and we're not getting quite as close to our adjustments. So that's how we would look at that. So again, we assess our loadings just like we would normal spectra. You can identify peaks and valleys and match them up with your wavelength ranges that you know where things are absorbing. The assessment of scores, you want them to be symmetrically distributed. And you look for relationships between samples. There might be sample groupings. You might find outliers in this case. And I'm getting some questions here. When do you do an SNV before doing a derivative? So I like to use that scattering effects to really drive which type of preprocessing I do. And I try to get rid of the maximum issues first. So SNV gets rid of multiplicative effects. And if I see something that has multiplicative effects, which is that fanning, then I apply my SNV first. The question is, why not use a baseline transformation? Which one is better, a second derivative or a baseline? So it's really going to depend on your data. I've played with this data a lot, which is why I went the way that I did. But we can do a simple baseline as well. I'm going to preview my results just to kind of get an idea of what I want to look at. We can do a baseline offset. You can add in a linear baseline correction as well, or just a linear baseline correction, whichever you think makes the most sense. In this case, I think just the linear baseline correction is appropriate. The proof is really in the pudding. If we analyze this, that is fine. Okay. It does okay, but you can see it takes a heck of a lot more factors, and we're still not getting down to that lower RMSCE. If we plot this, right, we can see there's still quite a lot of variation happening in our spectra when we just do that simple baseline offset or linear baseline adjustment. So it really depends on your data, and I tend, when I'm building models, I play with lots of different types of pre-processing, and you sort of get a feel for it. The thing with multivariate data analysis is that it's kind of a scientific art. There's no one correct answer, and you can apply very different approaches. We can also do some sample grouping just to see how those line up. Right, and so what you want to do is you're really trying to minimize the amount of variations that are in there that are not due to this change in Y or a change in the protein content. Okay. So some other things that we can use this for is you can actually monitor a process, a time-evolving process with your principal components analysis. If something is changing through time, so this is a chemical reaction, it's coming towards the end of the process here, and you can determine endpoints from that. In this case, we've got a drying process, and we can see if we build batches on top of each other, then we can see how they fall into this space. So I'm going to give a quick example of that as well. Not with that one. So this is data that was taken in a fluid bed dryer in a pharmaceutical process. It's NIR data going over time. And I'm just going to use the raw data at this point. I'll go ahead and plot it so you can see. It's all spectra. Actually, what we're going to do here is I'm going to choose an area here because we've got some noise on the ends, and I know that I'm trying to measure water, so what I'm going to do is actually create a sample range. So we're going to mark variables. I'm going to mark this with a rectangle, and I'm going to take this area here that I know contains the water bands, but it doesn't have a lot of noise involved with it. Being a little slow. All right. Now, once those have been marked, I can right-click and I can create a range, which is nice to have over here. So I have a reduced spectral area. I do want to make sure when I'm working with Spectra and I've made a column set, I want to right-click and make sure that this Spectra is clicked. And what that does is it makes the default plotting for your loadings and your B coefficients and PLS into line plots, because scatter plots don't make a lot of sense when you're dealing with spectroscopic data. Now for this particular data, I know that I need to do an SNV, so I'm going to do that now. And I'm only going to do it on that reduced range. That's very important. SNV is one that if the range actually matters, what you're looking at. Again, that's going to be a little bit out of the scope of this topic, but we can talk about pre-processing in another webinar. I'm going to plot these, my reduced range, take a look at it. And it's a little bit noisy, but we can play around with this for now. So what I'm going to do is I'm going to create some row sets that have not been done yet. I'm going to use 3 of these batches. I'm going to create a row range for training. And I'm going to use the other 2 for testing. I'm just right-clicking and I can do create these, so test. So now I'm going to do analyze, principal component analysis, just on my training set using my reduced spectral range. I have a question. If I have to look at a specific region of the spectrum for drug content analysis, would I need to do the pretreatment first and then choose that range, or would I take the specific range first and then do the pretreatment? So again, that's going to depend on the type of pretreatment you do. Something like a derivative, I tend to do across the entire range because it's not affected by what the range is. Something like an SNV, it looks at the range itself and calculates the mean and the standard deviation in that range. So if you do an SNV over a smaller range versus a different range, then you're going to get different output. So it really depends on what you're looking on. It's going to depend on your situation and which type of pre-processing you're doing. Okay. So now I have my PCA for my batch trajectory. I can see that it's very clearly a 2-factor model, which is very nice. If I want to look at both of the loadings up here at the top, I can put in the box 1 to 2, so that shows me what the 2 different ranges are. This makes a lot of sense because this main peak here, that's going to be a water peak, and this is also a water peak. And since we're monitoring drying, this makes a lot of sense. I can do some sample grouping just to make sure that my batches are following the same pattern, and they are. You can see that all 3 of these batches follow the same range. Now, someone was asking about the influence plot. In this case, I've got 2 samples here that seem to be outliers. Okay, if I go back to my sample grouping, I want to give it the sample names, and I'm going to put those on here. Okay, so in this case, we can see that this tends to be the beginning of our drying. So this is all A1, A2. C13s or so, B1s and 2s. So these are early in the samples towards the end of the samples, or the drying time. And these are later samples for C. So it could be that these particular data points, maybe they were collecting even after they stopped the drying. There could be something going on there. So what I might do now is, since I've selected those, I can right-click on my PCA node and recalculate without those marked samples. Since they are outliers, we're going to do that. Okay. It looks pretty much the same, so they weren't really gross outliers, but sometimes it's good to bring them out just in case there's some sort of issues in there. So now we can see that nice even path in 2 dimensions. Now we want to use our training set data to check that as well. Now, one of the things that you need to be careful of, and let me pull this over. Oh, I actually had a validation set. So we can go in, use our validation spectra. We want to predict a projection. I'm going to use my PCA1. That's the one that I liked. And all rows and all columns. Now what we see here is that the blue, that's our original calibration data set, and our green is our new projected data. And we can see they follow a fairly similar trajectory. You can see that as well in this residual variance. You can see that in the first PC that we are explaining almost as much with our new data as we are our original data. The blue and the red line is our calibration and cross-validation residual variance, and the green line is the new one. So I'm going to go back up in here, and I'm going to create a new one on my reduced data very quickly. Oops. I do this a lot. That's not what I meant to do, so I'm going to delete that. I actually want to use the entire range. Ah, dagnabbit. Pardon me. So it's showing that I have these particular rows selected, so it's automatically selecting those rows for the analysis. That's why I'm having a little bit of tricky time here. Analyze, principal component analysis, here. I want to do all rows and my reduced columns. Now it will do what I'm expecting. All right, so what I'm going to do, and this is kind of fun, so we can zoom in, and we had determined that this side of our spectrum, or of our scores plot, is where things are dry. So what I'm going to do is I'm actually going to mark the end here, and we can make a PCA model that's specific to the end point. If I right-click and recalculate with marked samples, tell it OK. Now we're going to have a PCA that is specific for the end point. We can just take a look at the groupings, and we see they all fall in here. So there's a little bit of difference in the batches, but we know, because these are our calibration data set, that they are good data. Now what I can do is take my validation spectra. You need to make sure that when you are predicting or projecting that you want to use raw spectra, because in the unscrambler, any sort of pre-processing that you have done is included as part of the model. So it will apply that pre-processing. So you make sure that you do use your raw data to do that. So we're going to do a projection on this final one that we did, on all data. Now this is going to show the entire batches, and we can go ahead and put our ellipse on here, and we can see this is not dry, it's not at the endpoint, not at the endpoint, but once it crosses over and stays inside this hotel T-squared ellipse, we can determine that it is definitely dry. So you can use this to drive your process understanding of what's going on and how to choose an endpoint in a qualitative manner rather than waiting for, say, limit of drying, which may take 15-20 minutes. And all that whole time that you're waiting for things to be dry, they might get over dry, you can have granules falling apart. So this helps you get some real-time analysis as it's happening. All right. Again, take a look at your components. When it starts to look noisy, there's probably no more information there, so move on. Oh, someone asked, do we not apply the same pretreatments to the test sample or validation sample? That's what I was just explaining. You don't manually apply them. They're actually part of the unscrambler model. Right? If I go in here and look at my PCA, I can see what the pretreatments are. It does an SNV transform over that minimal range. So it will choose the right range, apply the correct preprocessing to it. If I go back and look at my NIR wheat, one that had the, see here, we've got a second derivative that's applied, as well as an SNV transform. So it's part of the model. And if you apply the pre-processing manually, it will do it twice, which for some things that won't matter, like SNV, but if you're doing a derivative, if you're doing a second derivative and then doing another second derivative, you're essentially doing a fourth derivative on your data, and you'll get completely crappy results that you're not expecting. So again, we use our loadings plot to understand what's going on with our data. We can see in this case we've got some oils that are separating out, and one that is very different on our second PC. We can come in, look at our loadings for that second PC and see that it is this peak here. So that helps us identify what's different about particular samples. Here's just some examples of when we look at our scatter effects, how to determine what sort of pretreatments to use. Again, if you see this sort of general baseline offshift, and in the scattering effects, everything has the same slope and is just offset from each other, then those are additive baseline effects. If we see this fanning, that's showing that there is some difference in the scattering that is wavelength dependent, usually due to particle size. So that's when you need to do something that gets rid of multiplicative scatter effects. We have a ton of different pretreatments that you can use. Almost everything needs some smoothing to it. You can see that things get a little noisy. Sometimes it's okay, you can leave it in there, but you want to do as little pretreatment as possible to your data and still get good output. So this is just a quick summary of how you go through your workflow. You import your data, create your category variables, any variable sets and sample sets. Take the time to really think about this and do this properly. It'll save you a lot of time as you go through building your models because you won't have to redefine those ranges every time you do a new model. You make sure that you inspect and plot your raw data. That gives you some knowledge of whether you need to pre-process your data. And always do your PCA on your Spectra first. Just take a good look at it, understand if there are any groups, if there are any outliers, things like that. Then you're going to do your calibration and validation to determine which pretreatments are the best. Once you figure out which pretreatment gives you your best cross-validation, then you start applying this to test sets and maybe do some wavelength selection, and then you validate and interpret your final model. And then once you have your model, you predict new samples and you update as necessary. All right, I do have a bunch of questions here that we will try to get through. I have someone asking that they had a prediction set and got negative values. What could be the reason? It could be that you applied your pre-processing twice. That has happened a lot to me where before I realized how the unscrambler works and applies that pre-processing. It could be that your data is different for some reason if you have some offsets in your wavelength ranges. It's hard to know without actually really looking at your data. It could be that you have a lot of variation. If your prediction range, it runs from 0 or very low values to a very high value. It could be that there's just a lot of variability in those lower ranges, and in those lower numbers, it actually crosses 0. So there's a lot of things that could be happening there. Can you actually get information on the particle contents instead of just filtering this information away? Yes, so this is why you need to be aware of what your application is and what you're trying to what information you're trying to get out of your data. If you're looking for information about particle size, for example, you don't want to get rid of some of that scattering because that scattering is going to give you information about the particle size. If you're looking at other information, sometimes that particle size is actually noise. So you need to think about your problem and decide what is the information you are actually trying to get to. How do you do a wavelength selection? What does it mean? Wavelength selection is going to depend on your data. For example, let me open up this one again. I'm going to unmark these. Okay, so what I did in here is I know that for this particular data set, I'm trying to measure water. I'm measuring drying during a fluid bed drying situation. I know where the water peaks are in our spectrum. You can go to any sort of reference to find a NIR wavelength guide that will tell you the wavelength ranges for different types of chemical bonds. Water happens to be very common. It's in this 6800 wave number range and then down in about a 4800 wave number range. In nanometers, people tend to think of it that way. It's around 1400 nanometers, and I think it's 1800 nanometers. Because I know that's what I'm looking at, I'm focusing just on those ranges, on those wavelength ranges, because I know that the rest of the wavelengths don't really give me information about water. If I'm doing something with protein and I'm in the mid-infrared range, I can go in, I know where the amide peaks are. So proteins have nitrogen bonds in them. So I go to the areas that I know that have, that should be changing with respect to the thing that I'm trying to measure. That's how and why you would do a wavelength selection. Someone did ask me about hoteling t-squared ellipse. So generally what we do is a 95% confidence interval. There's a lot of different confidences that you can use. It basically opens up or closes this in. If you think about your traditional statistics when you're looking at a mean and standard deviations away, if you have like one standard deviation away, it covers like 68% of your data should fall in there. 2 standard deviations is 80-something. And then at 2.96 standard deviations away, you have 95% of your information should fall within that range. It's the same thing. What hoteling t-squared is that same kind of limit, but in multivariate space. What would be the typical wavelength range to expect water overtones in inorganic matter? Same thing. Water is going to show the same whether regardless of what type of matter you're looking at. So you're looking at that 6800 range and that 4800 range. And that is all that we have time for today. Thank you again for everyone attending and having some really great questions. If you have any questions that I haven't covered that you'd like to send me, my email is on the screen here, hbrook@camo.com. Feel free to shoot me any questions you might have, and I hope everyone has a great day.